This first talk in week 10 is to introduce the notion of covering map. And I want to do this because we need to talk about the fundamental group of the circle. And this is normally studied using an example of a covering map, sort of prototype example. That is the map that sends the real numbers to the circle. So that is the map which sends the real number t. By the circle, I think of the unit circle in the plane like cos t, sin t, but it's a bit more convenient to think of it as the set of complex numbers of modulus 1. It's the same thing. So that map, would, in that case, would take t to e to the it. So that map is an example of a covering map which satisfies the definition that's written out here. So in general, a covering map, it is only a sort of one-dimensional example, so it doesn't really give the full flavour of it. Covering maps are normally written vertically. So we're talking about a map from a topological space capital Z to a space X. The map here is called P. And the idea is that for any point in X, in the target, or sometimes called the base, we can find some open set around that point, so that the inverse image of that open set by P, we can find this set sufficiently small so that its inverse image in Z consists of a number of disjoint open sets, each of which is homeomorphic to this bottom one U. So there might be, say, V1, V2, V3. There may be infinitely many. There may be just two of them. But the point is, there could just be one of them if we took the identity map, but that's a bit stupid. So the idea is that we have these disjoint, for a sufficiently small sort of open set in the base, we have these disjoint, the inverse image is a disjoint collection of open sets. And the restriction of P to each one of these sheets, as they're called, gives a bijection, indeed a homeomorphism, from that sheet to the open set below. That's the notion of a covering map. So we're going to be looking at properties of these maps. But first of all, let me show you an example of something that's not a covering map. So here's an example, going back to really one dimensions. Let's consider, sort of use a graph here. Let's consider, let me take this to be the x-axis, but this to be the z-axis. So instead of y, I'm using z. Let's consider the map that takes z to z. So x takes z to z squared. So in other words, I'm defining x to equal z squared. So this is the equation of a parabola, but it's a parabola that's sort of this way round, goes to the origin. Of course, x is always non-negative. Now, the point is that clearly, provided I'm away from the origin and looking maybe at an open interval in this part here, then the inverse image of that does consist of two open intervals, small one there and a small one here. So the inverse image does consist of two open intervals in Z, each one of which is homeomorphic to, might have different lengths, but it's homeomorphic to the interval I had here. But if I go around the origin, if I take my point here, x to be the origin, then there is no inverse. If I take the inverse image of any open set around the origin, I'm going to get a single open set here, and that the map, the restriction of the map to this open set, this vertical open set, is not a bijection, because we have two values in Z that can go to the same value in X. So the problem is that the origin here doesn't satisfy the condition. If we were to remove the origin and just sort of restrict the map to the sort of positive numbers, X being strictly positive, that would be a covering map, but it's a trivial covering map in the sense that the sheets are globally disjoint. It's not very interesting. Okay, that's the notion of a covering map. So a bit of terminology, as I said earlier, these small open sets lying over the open set in the base, homeomorphically they're called the sheets, and I personally call an open set in the base with that property that it's covered by these disjoint sheets. I call that a mattress. That's just my terminology, it's not common. Another thing to remark is that when you have a covering map, as with any map, you've got an equivalence relation, because you can say 2 points of Z are equivalent if they map to the same point in the target. So we could say that any 2 points of Z are equivalent. Z is equivalent, whatever notation you use, to Z primed if they map to the same point. But in general, that won't, the topology of Z won't necessarily correspond to the quotient topology, but for covering map it does. So for a covering map, we have this notion that X is really the topological quotient of the space Z. So in particular, that means that a set in X is open if and only if its inverse image is open in Z. So remember, I've several times mentioned that notion of the quotient of a topological space by an equivalence relation. Here the equivalence relation would simply be, the equivalence classes would simply be the inverse image of the distinct classes, would simply be the inverse image of the points X, so that X is in X. Those are the equivalence classes in this case. Okay, there's some examples. So the primary example which I mentioned before is that of the map from R to the circle. I've changed the parameter here because I'm parameterizing the sort of circle from 0 to 1, but it's more or less equivalent to what I said before. So this map sends S in this case to 2 to the e to the 2 pi is. So before I had to go from 0 to 2 pi to go once around the circle. So if you think of this figure here on the right hand side, the idea is that you maybe later on will have a sort of base point. So this would be the point 1 if you think of a complex numbers. That's the point 1 on the circle. And if you want to map to that point, you maybe start here and you'd have to go all the way around one loop of this helix to map to 1. But you can see that if you take sufficiently small open sets in the base, for example, this open set in the circle here, around here, then its inverse image will be an infinite collection of open sets, but it will be a disjoint collection of open sets. So that's the notion of a covering. So another example is simply mapping from the circle to itself by just taking the complex number to the power k. That's a covering map. In fact, you can extend it to be a covering map on all of the complex numbers apart from the origin, but for the same reason as the parabola, it would go wrong at the origin, because the inverse image of the origin, whereas the inverse image of an arbitrary z, of a generic z, would be k points, because there is k roots. Once you fix z to the k over the complex numbers, there are k solutions to the equation. But if you map to the origin, only the origin to the power k. So if you map to 0, only 0 to the power k maps to 0. So there would only be one point in the inverse image, not k. So and you wouldn't get this bijectivity property. So that would be an example of something called a branched covering, which is a covering apart from over certain points. But we won't be spending much time on that. Partly because it's simpler to study the situation in which the space Z is simply connected, has trivial fundamental group, which S1 does not. But one other key example is that of real projective space. So the definition, if I take a sphere in n dimensions, the n-dimensional sphere, that means all the points in Rn plus 1 of unit distance from the origin, so the sum of the squares of the coordinates is equal to 1, that's the n-dimensional sphere, I can always identify, so a point of the sphere I think of as a vector, or doesn't matter whether it's a row or column vector, I can always identify that vector with its minus. So if I identify V with minus V, that's an equivalence relation, and it defines a new topological space in which, as I say, each vector is identified with its minus. They correspond to the same point, sort of thing we did with surfaces. And that quotient topological space is, by definition, a real projective space of dimension n. And as I'll explain again later this week, you can get the same, topologically the same space by, instead of taking the n-sphere, you can take an n-dimensional disk. So instead of taking the ordinary 2-sphere, I can take an ordinary disk, and the interior of the disk plus its boundary, but identify opposite points on the boundary. That would give you the same space. Of course, if you do that for S2, I've just described a surface we called P, which of course I called the real projective plane, which is what it is. But you also have that alternative model. So that mapping from the sphere, which incidentally is simply connected, its fundamental group is trivial. I sort of explain that for S2, but it's true all the spheres of dimension at least 2 have trivial fundamental group. So the mapping from that sphere to real projective space is a covering map. It's what's called a double covering, because the inverse image of each point, there are just 2 points, namely a vector and it's minus the vector. Okay, so we'll be coming back to that example. Moving on. So now I've got some more technical things to be talking about. And it's a good idea really to have this picture in mind of the sort of real numbers spiraling over the complex numbers. Sorry, over the circle. So we've got this sort of spiral over the circle. And so that's an example of a covering map from R to S1 in this case. So there's this notion of lifting a map. So here, let me also draw a diagram. So we have a covering, and this is R goes to the circle. More generally, we would have Z goes to X. And we suppose we have another map here, which is called Y. And we have some mapping from the space, topological space Y, to the space X. Then a lift of F is, and you could do this for any spaces, but I'm thinking of that this is a covering map here. A lift of F simply means a map from Y lifted up, because you think of Z as vertically above X, lifted up to Z, so that when you do, you can get F by doing F tilde followed by P. So that's this equation here, so the triangle commutes. So that's the definition of a lift. And by the way, when I talk about maps from now on, it's always intended that they'd be continuous maps, because all the spaces are topological spaces. Remember, continuous just means the inverse image of any open set is open. So that's the notion of a lift. Now, if we just go back to this familiar example, suppose you had a path in S1. So a path is a map it's really a map from S1 to S1, but a path is a map from the interval to S1. A loop would be a map from S1 to S1. Suppose we have a path in the circle that maybe starts at this point 1, which I mentioned before. Think of that as our base point. Then, you can imagine a path might set out in one direction. It has to stay on the circle, but it may go back at a certain point and so on, wander around. The point is, it's clear that there's a sort of unique way one can lift that map to the real numbers, because if I can start anywhere, I could start at, say, 0. Suppose this is the 0 in the real numbers, this point here. The negative numbers go below, so this would be, well, first of all, I ought to say what the I mean, let me just, I mean, the map here would send, let's stick to the map that sends S, not T. Let me send the second map. So S, if I need it, let me say that S is going to e to the 2 pi is is the point of the circle. So if I want to do one full turn, it would be, I would be going to 1 here. So one would lie over, and this would be -1, for example, with that parameterization. But you see, if I want to lift this map, I could start anywhere I wanted over 1. I could start at 0, but then I don't really have any choice. If I want to sort of lift this path and describe a continuous map from 0, 1 to R so that this commutes, I have to sort of go along this part of the, I've drawn this the wrong way, I guess. Maybe this should be sort of -1 and this should be +1 the way I've drawn it. Sorry about that. So if I want to sort of go over this point, I have to go in this direction to sort of follow exactly this this curve, and I don't really have any choice about what I do. So that's the idea, that you can sort of uniquely lift, in this case, a path to Z, which is called the covering space. So I've defined that before I've really stated what I'm trying to say. But I've tried to give you the idea that there's a unique way of lifting. That is, if the space Y is connected, as was in the case, I was just doing the case Y is equal to 0, 1, that's obviously connected. If you have a lift, then it's unique. If you are able to lift your map, it's unique. Any two lifts, provided you start at the same point. So if they agree at one point, let's say, then they're equal, they agree at all points. That's the proposition. And I'm going to prove this proposition. I gave you the idea intuitively. Let me try to prove this proposition. So let's suppose we have two lifts, and I don't know if you can quite see this, so it's quite customary to denote a lift of a map F by F tilde. Here I've got a second lift, so I've denoted that by F hat, or some people would call F roof, this symbol. That's a distinct lift. F hat, I'll call it. So I've only drawn one half the hat because my connection is slow. There's F hat. So suppose we have two lifts and they agree at one point. So remember the diagram again. We've got Y mapping into X, and we've got a path, we've got a covering space Z covering map P, and we're trying to, well, we have got two lifts from Y to Z, namely F tilde and F roof. And they both have the property that they commute, the diagram commutes. So when you compose P with either of them, you get the same map, which is the original map F. So what we do is we look at the set where these two maps agree. We look at the set in Y where these two maps, F tilde and F hat, agree. And we know that's non-empty because we're assuming that they agree at least one point. So what's the idea? Well, since they agree at one point, say this point Y, then that point Y, so they agree at one point of A. So the image of that point let's say this is not quite right, it should be Y, it should be F of Y, F tilde of Y would be in VI, some I, but they agree at that point. So it's that F tilde of Y is the same as F hat of Y. They agree at this point Y, so this point Y goes to, let's put it here if I can squeeze in, this point Y goes to a common point in Z, and that point we know will lie in some sheet VI, which is homeomorphic to an open set of f of y in x. That's the picture. But the point is, because these two open sets are homeomorphic and the functions agree at this point here, and because P is a bijection restricted to these green open sets, then these two functions have to, because of the lifting property, because of this equation here, that the two lifts satisfy that equation, they have to agree on all of VI. And therefore, when we take the inverse image of VI by each of these two maps, this open set, these are both open sets, then this intersection has to belong to A. Okay, so in fact they agree. So they agree on some open set of A, and that means that A is an open subset of Y. Okay, so A is an open subset of Y, but then we could also look at points, the complement of A, that is a point of Y where the two lifts disagree. And if they disagree, then it must be that one image is in one of these sheets and one image is in another of these sheets. And then by taking the inverse image of those two sheets, those disjoint sheets, you'll show that in fact we can also put an open set in the complement of A. So the set A at this point is both open and closed. But if it's both open and closed and it's non-empty, that contradicts the fact that Y is connected. So that is somewhat technical, but that is the argument that explains why any two lifts have to, if they agree at one point, they agree everywhere. Okay, and I can apply this in particular to the case in which Y is the unit interval, and so the map F is therefore a path, or maybe even a loop, into X. Okay, the last slide is, I'm afraid, as technical. This explains that, I mean, we want to look at the special case in which we have loops. So again, we have the same setup. We have Z, which is covering space of X, and we have two loops, well, one to begin with, to be honest. We have chosen a base point, and we have a loop in the space X, call it alpha, and I want to try and lift alpha to Z. So I want to ask, can I lift that map as a map from the interval to Z? So this is a loop, so it starts and finishes at x0. Now I've fixed a point in the inverse image of x0. So this is a covering map. So the inverse image of x0, there may be several inverse images, or maybe an infinite number of inverse images. I've chosen one Z. Just as before, when I did the real numbers over the circle, I chose 0 as my starting point. I might not have a sort of distinguished point to start at, but I can choose one and call it Z. So that will be my base point in the covering space Z, capital Z. So the statement is that I can find a unique lift of this loop alpha, which will be a path. It won't in general be a loop, it will be a path because it will be a continuous map from 0, 1 to Z by definition, and it will start at little z. So in other words, I can find a lift with the property that alpha tilde, and it's going to be called alpha tilde of Z, subscript Z, because it's going to start at Z. That means alpha tilde Z at 0 is equal to Z. That's part of the definition of this lift. So I'm asserting that I can find such a lift, and I really showed you why that was fairly obvious for R going to the circle, because once you move around the circle, you've got no choice as to what you do in the helix. You've got to follow along by continuity. You can't jump. So in the helix, you just got to follow continuously around the helix so that it maps back to what you're doing over the circle. Now, before I explain why this is true, let me give you the second part of the theorem, which is an analogous statement for homotopies. So this is why I need the second loop. So if I have two loops which are homotopic, then there's a homotopy of loops, which means that we fix the endpoints, that the homotopy has to preserve those endpoint, the end point, which is the base point x0. So we get a family of loops all based at x0, deforming alpha into beta. If you have such a homotopy capital F, then there's a unique lift of capital F. So again, let me draw the diagram of maps. We have Z mapping to X. This time we have the unit square. I'll just draw the unit square, which is I2. We have a homotopy which maps that into X. And remember, we have our base point, which for the circle is just the complex number 1. We have our base point here, and the homotopy must map all of this vertical edge there, and that vertical edge there has to map into x0. The image of this edge here corresponds to alpha, and the image of the top edge corresponds to beta, because we have a homotopy between alpha and beta. F is the homotopy that gives the equivalence of elements alpha and beta in the fundamental group of capital X. And the claim is that I can lift that map. I can lift that map, capital F, so that, as before, remember, as a lift, it means that when you do F tilde and then you follow that by P, that will just be the same thing as the homotopy capital F. But the interesting thing is, what is the lift going to do to these loops? Because typically, if you lift a loop, it won't stay as a loop, because you have to start at the given point. So we've chosen in Z some base point. So when we lift alpha, for example, we'll have a loop we'll have a path that starts at Z and it will wander around, but it won't necessarily finish at Z. It will finish somewhere else. It has to finish somewhere that's lying over x0. But remember, they're these sort of separate points. There's Z and they're these, shouldn't really, well, let me get rid of the line. Lying over x0, there will typically be a number of points, finite or infinite number of points. And our path, when we lift the path alpha, it may wander, if it starts at Z, it may wander around, but it has to finish at one of these points that maps to x0, but it won't necessarily finish at Z. So it will finish at a point which sorry, you can't see anymore. It will finish at a point, there we are. So there's the loop alpha, which is finishing at some other point, possibly, that lies over x0. And that other point, therefore, this will be the lift of alpha. Alpha is the loop downstairs. We have a lift of it to capital Z. And if the lift is starting at Z, we call it alpha tilde Z. But where it finishes will be denoted by alpha tilde Z of 1. And in this case, it's this point there. Here. So what I'm saying is that in any case, we can also lift this homotopy. If we have a homotopy between alpha and beta, we can also lift this homotopy F tilde. And how do we do that? Well, first of all, I've got to prove part 1. I haven't even proved part 1 yet. So how do we prove part 1? Well, you need a lemma in topology, strictly speaking. It is not a very difficult thing to imagine. But you see, to prove part 1, we have a mapping from let's call it alpha. We have a loop in X, so let's call that alpha again. So remember, alpha in this case is a map from 0, 1 into X, and we want to lift this to Z. Well, the point is we can always arrange, we can always divide our interval. Here's the interval 0 to 1 pictorially. We can always divide it into a sufficiently large number of small intervals of a given length, with the property that each of these little intervals lies in what I call a mattress. So each of these little intervals, so the curve, the image of alpha will lie, of this little interval there, will lie inside one of these matrices over which we have these homeomorphic copies. And then obviously we can do our lifting, because if we start, well, should have really started at the beginning from 0. So let's suppose that this one is the first one in the list. So I can start there, and then if I want to start from, say, Z will be in this sheet here, Z over this, this will be X0 in that case, and I can start with Z, and then I've got no choice as to how to lift it, because I'm only constrained. I can't jump around. We have a continuous map, so I'm constrained to start in this sheet. And then I get to the end point of that interval, so I come to look at the next little interval here, and that will be contained possibly in some other mattress. So then I can continue, and I can keep going in that way, and the lift will be unique. That's the idea. Now, there's only a technical thing given by the asterisk. You need something like Lebesgue's lemma, something called Lebesgue's lemma, to prove that given an open covering, we have this. We know that each point essentially of our interval from 0 to 1 will be contained in some open set that maps into mattress here. But then we can get a finite subcover, because the closed interval 0, 1 is compact, so we can get a finite subcover, and then we just have to arrange that we can find a collection of intervals. We can find a length small enough so that each of these intervals of those lengths will, arranged in this way, will map inside one of those open sets. And that can be done using something called Lebesgue's lemma, but anyway, Lebesgue number rather of a covering. But anyway, that's how you lift intervals. And you can lift homotopies in the same way. So that's explained here in part 1 for the path lifting. For the lifting of the homotopy, capital F, you do a similar thing, but you have to divide the square this time. We've no longer got an interval, we've got a square. So let me try and illustrate in this little corner here. The domain of our mapping this time is a square. And it turns out we can also divide this into sufficiently large number of smaller squares or rectangles, so that the image of each of these will lie in a mattress in X. Now, again, we can start with this little rectangle here. We've got our original homotopy F, but since the image of this lies in a mattress, we know how to lift it. So we can lift that one, and then we can join up with this rectangle, and we can lift this one and this one and this one and go upwards. And then when we're done with that, we can go across here to the next one. We can lift sort of one column at a time. So that explains how we can lift our homotopy. Again, we need a sort of Lebesgue number of a cover, but that's a technical point which I'll sort of gloss over. We can certainly lift our homotopy capital F. Now, when we lift our homotopy capital F, the important thing to realise is that if you go up a vertical line in this domain, so that corresponds to a fixed value of S, if you like. So at the bottom we have our loop alpha, but when you're trying to lift a given point in X, you can't really jump around. So the lifting, since this is going to be a continuous mapping, when you project it down, it's lying over a given point, so it can't jump around. So this homotopy, when you lift it up, it has to be constant on all these vertical lines. So in particular, it's got to be constant here, and it's got to, the lift, since we're starting it at Z, it's got to stay at Z. So everything in this vertical line maps to Z, not necessarily in this one. So that means that when we've lifted beta, this top, remember, sort of will therefore correspond to the map beta tilde at Z, because it is starting again from Z, because we have constancy on this vertical line. But then that means that beta Z tilde of 1, which is the image of this point, this has to be the same as the image of this point here, which is alpha Z tilde of 1. So these two points of Z have to be equal. So I'm no longer on the proof of the theorem. I'm going forward. That's a property really of this lifting which I've made. That if we have a homotopy, so let me just sum up. If we have a homotopy between two loops in X, then when you lift these two loops, each of which you can lift the homotopy, so there'll still be the lift of these two loops will be two paths in Z, both starting at the same point, but the point they finish at has to be the same. Although they're not loops, they're paths, they have to finish at the same point. So the conclusion here is this very important corollary, which asserts that if you lift a loop in X to the covering space, then its endpoint only depends upon the class of the loop alpha in the fundamental group of X. Okay. That is the key conclusion I wanted to arrive at in this first segment.